Hello. Welcome to another Chem 100, another week of Chem 100. We are week 10 now, so really just 6 weeks to go. We're really getting toward the end of the class here. So from here on out, it's going to be less kind of fundamentals of how atoms and molecules interact. We've really kind of talked about that. And it's going to be more applied. So we'll talk about solutions and mixtures, and then we'll get into biological molecules and systems and all kinds of good stuff. So we're going to get started with that today, talking about solutions and mixtures. So as with many of our units so far, everything that we've done previously kind of builds up to what we're going to talk about now. So we can't really talk about solutions and mixtures without talking about electronegativity and polarity. So quick review. Electronegativity generally increases as you go up the periodic table and to the right. We've seen this before. We know that fluorine, which is right here, is the most electronegative element in the periodic table. So anything that's kind of going up that way toward fluorine and over here is increasing electronegativity. And then we can make polar bonds, polar covalent bonds, when we have two atoms bonded that have a difference in electronegativity. All right. So why is that important now when we talk about solutions? Last chapter, when we talked about polarity and intermolecular forces, we looked at things like hydrogen bonding, and we said that we have to know about polarity because certain types of atoms and molecules can have stronger interactions in between each other, like in solids and liquids. If those forces are stronger, so that affects things like boiling point, viscosity, vapor pressure, all of that. Well, it also affects how things mix together. And you might have heard the term like dissolves like. That refers to polarity. And we're going to see that it's a little more nuanced than that exactly. But basically, things with the same types of intermolecular forces can mix easily, and things with different types of intermolecular forces don't. And the reason for that kind of makes sense when you think about what we learned in the last chapter. So let's draw it out a little bit here. Grab another page. So let's imagine we want to put something like, we've got something like water. So remember our depiction of water is going to be something like this, where we've got these nice hydrogen bonds connecting water molecules in various ways, always oxygen to hydrogen, and they kind of make this big network everywhere. So this is water. This is a sample of liquid water. All right. Now let's say we want to dissolve something in there. Well, if we dissolve something else that is also polar, so let's mark our polarities here. So we've got some minus by the oxygen and some plus by the hydrogen. That kind of all goes all around and down here as well. We'll just do that for now. So let's say we have another polar molecule. Let's just call it HX. X isn't an element, but it's something else that has a polarity difference here between hydrogen and whatever that other atom is, so that we have a negative and a positive, just like with water. So you can imagine now, if this is HX, that this can fit pretty nicely into this water matrix. It would have to kind of flip around here. Flip it around. But we could say, all right, let's say this hydrogen bond breaks, or this water molecule just kind of moves apart from it. And then we could imagine putting that HX molecule kind of in here, with the negative side facing the hydrogens and the positive side facing the oxygens. And now we can make some new intermolecular interactions with the HX that would fit in really nicely, because we still got negative, positive, negative, positive. So we're still having that same kind of idea where negative and positive are alternating and then therefore attracting each other in between molecules. So that fits in very nicely. And so this is what happens why we say like dissolves like. If we have another molecule with similar intermolecular forces, even if it's originally kind of all tied up with its own forces, like this, these are the same types of forces, so they can be broken, and water molecules can fit in, and all this stuff can mix very nicely into what we might call a solution. We'll define that a little bit more in a bit. But let's say we've got something different now. Let's say we're now dealing with something that is nonpolar. Well, a nonpolar sample might be, some carbon and hydrogen or something like that, something like this. Where there is no positive or negative, but instead we have these dispersion forces. So this is, let's just kind of draw it as like a blob, and let's pretend there's more blobs, and they all kind of stack on each other using those induced dipole forces that we defined last week. And so these are a different type of intermolecular force. These are dispersion forces holding these things together because they're nonpolar. They're not really positive and negative in the same way. And so in order for these things to fit in the water matrix, first of all, that nice hydrogen-oxygen positive-negative attraction would have to break. And then all of these dispersion force interactions here would have to break. And then these things would have to kind of fit themselves into the water molecules. And that's just energetically not favored. Those things would like to stay with themselves. They have more energetically favorable interactions if the water stays with the water and this is propane, the propane stays with the propane. So mixing doesn't give them any energetic advantage because these are nonpolar and these are polar and they have different types of interactions. So that's why when we put these types of samples together, they don't mix. When we have different types of intermolecular forces, they don't mix well. When we have the same types of intermolecular forces, they do mix well. And that's where we get that term, like dissolves like. All right, so let's look at solutions. Solutions are homogeneous mixtures. We talked a little bit about that definition way earlier in the semester. And they're combined so evenly throughout that it's all the way down at the molecular level. So there's, as we just drew, there's individual molecules kind of surrounded by molecules of something else. Now, a solution is going to have two parts. Well, maybe more, but it's going to have solvent and solute. And we have to be careful about how we define these because we're so used to water solutions that we often always say, oh, well, water's the solvent, and then whatever solid you put in is the solute. And that usually is true in those cases. But the actual definition is just that the solute is the thing that there's less of, and the solvent is the thing that there's more of. Because it turns out there's lots of different types of solutions, and they're not just liquid with a solid dissolved in it. So let's look at some of those examples in the table here. The first row is one of those examples. In fact, the first couple rows are where we would dissolve some solid solute, like 5 grams of sodium chloride, in water, say 50 milliliters of water, and we make salt water, and that's a solid in a liquid solution. We could also dissolve sugar in water. We'll talk a little bit about what the difference is with those solutions. But then as we move down the list, you can see some other types of solutions that are not solids dissolved in a liquid. So for example, brass and bronze are examples of metal alloys where one metal is dissolved in another metal in a molten state, but then it's solidified, but it's still a solution. So brass is a solution of a copper solvent with some zinc in it. There's some other stuff in there too, but that's the main idea. And then bronze is copper with some tin solute in it, and those are solids in a solid. You can also have liquids in a liquid, like vinegar, which is acetic acid dissolved in water. And I think this is actually, yeah, that might be right. Okay, yeah. So acetic acid dissolved in water gives us some vinegar. You can also have, alcohol dissolved in water, like whatever percent alcohol solutions that you might have. You can have gas dissolved in a gas. Air is a solution. It's mostly nitrogen. That's the largest component of air. But there's also oxygen, and there's other types of gases in there, water, carbon dioxide. And so air is a solution as well, a gas in a gas. And then you can have a gas dissolved in a liquid. You can take carbon dioxide, you can dissolve it in water by bubbling it through the water, and you have a gas dissolved in the liquid. In the ocean, right? Fish have to breathe oxygen by getting it from the water. So that oxygen is not little bubbles of oxygen floating in the water. That's actually oxygen molecules that are dissolved into the seawater, and that's where they're getting their oxygen from. And then in a very kind of a unusual one, you can have dental amalgam, the silver filling stuff, where mercury, which is a liquid, is dissolved in silver as a solid. And so by tweaking the amounts of those, you can have it melt and solidify at exactly the temperatures that you want to. All right, so there's some examples, and there's some, I would say, relatively simple questions here. Is this always this? Is this always this? And often, well, I think for all of these, the answer is no. And generally in chemistry, when we say this is always this, the answer is no. Or is this always this? The answer is no, because there's always exceptions. But in this case, it's not just exceptions. The definition is broader than what we usually think. All right, I do want to look at this question number 7. Is the solute always a bigger or smaller amount than the solvent? So the solute should always be a smaller amount than the solvent. But again, there's always weird extra stuff going on here. So we're going to say this is generally yes, but one exception here is water solutions. Water is such a common solvent that sometimes even when there's more of something else than water, we still call water the solvent. So for example, if you had a very high concentration alcoholic drink like whiskey or something, and it might be 55 or 60% ethanol, alcohol. That's actually more than 50%. So there's more alcohol in there than there is water. But we still call it a 55% solution in water because water is such a common solvent. We often keep it the solvent even when there's more of something else. So that's just kind of a weird exception that sometimes happens. All right, so you can identify some solutes, solvents here. Okay, a couple more definitions. Whoa, went too far. And I believe we'll have a demo for you in lab on this this week and next week. Electrolytes. You may have heard this term before. It's usually associated with things like sports drinks. What are electrolytes? Well, electrolytes are compounds that dissolve in water and make it conduct electricity very well. So a strong electrolyte is a compound that conducts electricity very well in water, which means often that it dissociates completely into ions. So if you have sodium chloride, NaCl, as a solid, and you dissolve it in water to get sodium chloride aqueous solution, what that really is totally separately dissolved sodium ions and chloride ions. So when you dissolve sodium chloride in water, and there's a picture of this in the previous notes in the handout from last week, H9, when we talk about ion-dipole interactions. The sodium and the chloride ions are completely separated from each other and surrounded by water molecules. And because the substance, sodium chloride, has totally broken up into ions, that solution is going to conduct electricity very well because the ions can move in solution to conduct the electricity. So any kind of ionic compound that dissolves in water and breaks apart fully is generally going to be a strong electrolyte. Another group of strong electrolytes are certain acids, such as HCl, hydrochloric acid, nitric acid, sulfuric acid. These also, they're not ionic exactly, but the hydrogens break off in solution. And we'll get into this more in the next chapter when we talk about acids and bases. That also produces a strong electrolyte. And so in fact, when we talk about strong acids and bases versus weak acids and bases, this is again in the next chapter, we're really talking about whether they are strong or weak electrolytes. It has nothing to do with how dangerous they are or like how corrosive they are or anything like that. And then non-electrolytes are compounds that do not conduct electricity in water. So, for example, sugar. Sugar is, well, I mean, there's various types of sugar, but sucrose I believe is C12H23. Oh, no. Hold on. I don't think, wait. Yeah. C12H22O11. So this is table sugar. And this is a covalent compound of carbon and oxygen and hydrogen. And when you dissolve it in water, the sugar molecules separate from each other and get surrounded by water, but they don't break apart into ions. So sugar water does not conduct electricity because there's no charged particles, there's no ions or other charged particles in the water. There's just neutral sugar molecules. So things that dissolve in water but do not produce ions are non-electrolytes. And then in the middle, you have weak electrolytes. There are compounds that dissolve in water and break apart a little bit, but not enough to make a lot of ions to conduct electricity very well. So these are things like acetic acid, some other types of acids, some ionic compounds are weak electrolytes, but certain compounds don't break apart well. And there's not really a great way of looking at a compound and knowing what kind of electrolyte it's going to be. But you can generally guess that a strong electrolyte, if you have an ionic compound that dissolves in water, it's going to be a strong electrolyte. If you have a covalent compound that's not an acid that dissolves in water, it's going to be a non-electrolyte. And then the weak electrolytes, like maybe some weird stuff in the middle. But there's not really a way of knowing those just by looking at formulas. All right, so a few more definitions here. Unsaturated, saturated, and supersaturated. So now we're going to start talking about how much solute per solvent in a solution. So if you have just pure solvent, you don't have a solution yet, and you start putting the solute in, you have what's called an unsaturated solution. There is less solute than the most that you could possibly put in when you first start adding it. At some point, you will get to the point where that solution is saturated, and that is where you have all the solute the solution can. Well, what does it mean, can? Well, it means that if you were to put one more piece of solute in that solution and try to dissolve it, it would not dissolve. It would simply sink to the bottom or float, depending on what it is, float around, and it would not dissolve into the solution because the solution has already absorbed all of the solute that it can, and that has to do with how water interacts with these particles and all that kind of stuff. So a saturated solution has the most solute that can possibly be in there. Except there is something also called a supersaturated solution, which is more, and like this doesn't even make sense, holding more than all the solute the solution can. How could it possibly hold more than the most that it can? Well, if you treat it in a very specific way where you heat it up and you dissolve the solute under increased temperature, and then you very, very carefully cool it, you can actually trap more solute in the solution, but that's a little special. It's a special circumstance. And so if you try to put one more crystal in a supersaturated solution, not only would it not dissolve, but it would actually precipitate a whole bunch of other crystals out with it. And so if you ever have made like rock candy or something like that, or if you've made candy at all and you're cooking the sugar up at high temperature and you have to be really careful not to form crystals around the sides, this is part of that reason, is as those crystals they pull other sugar out of solution with them. So we can graph this and we can look at how different materials behave in different temperatures. So let's take a look at this graph, make it a little bit bigger here. So in this graph, we have on the x-axis down here, we have temperature. So this is just as you go from left to right, you're getting higher in temperature, heating it up. And then the y-axis is our grams of solute per 100 grams of water. So how many grams are in water? And these are, and so the plot is plotting the saturated solutions, which is also known as the solubility. So as an example, let's look at somewhere where it's really nice and clear, like where one of these lines crosses right at a corner or something. I'm not seeing. Well, okay, here, this will be. Let's look right here. Everybody can see that. So we're on this ammonium chloride curve, NH4Cl. And so what this point means right here is that if we are at 50 degrees C, if we heat up our solution to 50 degrees C, we can expect to dissolve 50 grams of solute in 100 grams of H2O, of water. So we can dissolve 50 grams of ammonium chloride in 100 grams of water. Another way of saying that is, at that point, at 50 degrees C, the solubility of ammonium chloride is 50 grams per 100 grams of water. And so now we can look at that curve and we can think about what happens when the temperature changes. So as the solution cools, the curve goes down. And by the time you get down to just below 30 degrees, the solubility has dropped to 40 grams per 100 grams of water. So that means that only 40 grams will dissolve in those same 100 grams of water at lower temperatures. So if we were to actually do this, what we would expect to see is some of that excess ammonium chloride precipitating out of solution because it's no longer soluble. We're now above the solubility. In the other direction, if we heat this up, we can see that the solubility increases. So as we get higher and higher temperature toward the boiling point of water, we can dissolve more and more ammonium chloride. And then ignore the dashed lines for now, but the solid lines, you can see that different solutes have wildly different behavior with respect to temperature. So something like potassium nitrate, KNO3 here, even just heating it up a little bit drives the solubility up substantially. Whereas sodium chloride is much flatter. Heating it up doesn't really have quite as much of an effect on the solubility. You can kind of try this at home next time you're cooking. Notice how much sodium chloride you can dissolve in a bit of cold water versus a bit of hot water. It's not that much difference. And then do the same experiment with sugar. Sugar is not on here. These are all ionic compounds, but sugar has a very steep curve like this potassium nitrate. And so as you heat up the water a little bit, you can dissolve all of a sudden a lot more sugar. If you ever tried to dissolve sugar in like iced tea versus hot tea, for example, it goes into the hot tea a lot more easily because of that higher solubility. So most solids behave like this, where as you heat them up, the solubility increases. Some of them do it very gradually, like NaCl. Some of them do it very sharply, like KNO3. Some of them are weird because there's always outliers, like sodium sulfate. The solubility actually goes down with higher temperature. But that's unusual. Generally, solids increase solubility with temperature. Gases, however, generally do the opposite. So you can see here HCl gas, NH3 ammonia gas, SO2 gas. These are all lowering their solubility with higher temperature. And if you've ever dealt with CO2 dissolved in your water, like if you've had a soda that was in the fridge versus out on the counter, you lose that carbonation a lot faster out on the counter because of the higher temperatures. The carbon dioxide is not going to dissolve quite as well. So there are some questions here as you work through these just to kind of check that you can read the graph and how all that stuff works. I think you'll be okay with that, but of course, let me know if you have questions or issues with it. And then the last thing we're going to talk about today is how to calculate measures of concentration. Are there? And we're going to look at two calculations. We're going to just introduce them a little bit today, and then I'll let you go do some practice on the handout here, and then on Wednesday we'll come back and go through some of those problems. So the tricky part about concentrations is measuring how much solute is in there, because up to now, all the things we've been measuring have been pure substances. So if you take some solid, you can just weigh it and you have that much solid. If you have a liquid, you can measure a volume and you have that much liquid. Even with a gas, if you know the pressure and the volume and the temperature, you can figure out how much gas you've got. So when we have mixtures now, it gets a little bit trickier because the amount that's in there is going to change based on how much total solution you have. But the ratio is not. The ratio of solute to solvent is always going to be the same. And so that's how we generally calculate what we call concentration, the measure of how much solute is dissolved in a specific amount of solution. And there's lots of different ways to measure concentration. We're gonna focus on two of them in this class, mass percent and molarity. Excuse me. Mass percent is also sometimes called percent by mass. It is simply a percentage of the total mass. So I think conceptually this makes a lot more sense. You have a solution, it has a particular mass, the solute is some percentage of that mass. So a 5% by mass solution means the total mass is 5% solute and 95% solvent. Excuse me. The other measure that we use that's really important in chemistry, but sometimes less so in other areas, is molarity, where we look at the moles of solute per liter of solution. And the reason that this is important here is mass percent is based on weighing, it's based on the mass. Molarity is based on counting. So if you care about how many particles are in solution, mass percent doesn't really help you out a whole lot. You need something that's actually counting the particles, and that's what moles do. So that's important when you're doing a chemical reaction. It's also important in things like bodily fluids and osmotic pressure, which we're going to get into on Wednesday, because that actually depends on the number of solute particles, not how big or heavy they are. So for many of these, you can either just use these equations directly, or you use them as conversion factors. But let's do a couple practice problems, and then hopefully you'll see how that works. So we're going to add 20 grams of sodium chloride and 100 grams of water, and we want to calculate the mass percent of the solution. So we want to know, of this solution, what is the percent that is solute, that is sodium chloride? So to calculate that, we can go back to our equation here, and we can see that is the mass of the solute divided by the total mass of the solution, and then that's a percentage. So we've got 20 grams of sodium chloride on top. And the bottom, we want to be the entire mass of the solution. So this is going to be 20 grams of sodium chloride and the 100 grams of water. So one common mistake I see in calculating mass percent is simply dividing the mass of the solute by the mass of the solvent. That's incorrect. It's the mass of the solute divided by the total mass of the solution. And then this becomes a decimal, so we multiply it by 100% to make a percentage. And we end up with 20 divided by 120, which is about 16.7%. If we're sticking with three significant figures there. All right, so now we're going to do the same thing with molarity, but it's going to be a little bit trickier now. And I'm just going to give you a little warning here. This is a legitimately difficult question that we're going to talk through, and I'm not expecting you to be able to solve. So if we have 20 grams of sodium chloride and 100 grams of water, what would the molarity of the solution be? Well, molarity is a different equation. It's moles of solute divided by liters of solution. It's not a percentage. It is just has its own units called molar, capital M. So instead of knowing the grams of sodium chloride, we need to know the moles. Now that part we can do. We can go 20 grams of sodium chloride, and we want to multiply it by a factor that goes from grams to moles. We talked about this a couple of units ago. That is the molar mass. So we look up sodium and chloride on the periodic table here. And just for simplicity's sake, I'm going to, oh, it's too small. I'm just going to say 23 and 35. I know it's not quite right, but All right, we'll add the 0.5. So 23 and 35 is 58.5 grams per mole. And so by dividing 20 by 58.5, we can get the amount of moles. So that's how many moles of sodium chloride we have. Oh, whoops, sorry, hold on. Okay, that's how many moles of sodium chloride we have. So that's our numerator. Great, we've got that. So now we just need the liters of solution on the bottom, and that turns out to be really difficult. The reason being that we know we have 100 grams of water, we know we have 20 grams of sodium chloride, but we don't know how much volume that is. We don't know, water by itself, that's easy. We can say 100 grams is 100 milliliters. But when we add that 20 grams of sodium chloride, the volume is going to change, but not by 20 milliliters. It's by something else, because the sodium chloride is all going to go into solution. So we don't actually know this. You could figure this out. You could go and look up density tables for salt solutions in water, and you could figure out, okay, if you've got 120 grams of a 16.7 mass percent salt solution, here's how much volume that should take. But you'd actually need all that to solve that answer. So just with the information here, there's not enough information to solve for molarity. So generally, when we're doing that, we're going to be given a different type of a problem. So I'll let you practice some of these. Definitely look at the examples in the book that are linked here before you try these, and see how they go. And then we're going to go through these and talk about dilutions on Wednesday and the other tonicity and stuff like that. So I'll see you Wednesday morning. Hopefully this was a good start for solutions, and let me know if you have any other questions. Thanks, everybody. Bye.